All right, now we can talk about vapor pressure that I was talking about earlier so that we can eventually talk about the boiling point, okay? Anytime you have a closed container with a liquid in it, we know that there's always some number of molecules that have the ability to be in the gas phase. So there's always going to be some vapor above the liquid. Right? That vapor's flying around at some speed and banging into the walls with some force, and so that exerts some pressure. Right? And that is what we call vapor pressure. Okay? Yeah, so exactly right. That's why we smell the things that we smell, right? Because those molecules have enough energy to be in the gas phase and when we breathe them in. So yeah, we can define it as the pressure exerted by a vapor over a liquid in a closed container. Okay? And we know that happens because we have that distribution of speeds. We have some molecules that have enough energy to be in the gas phase at all times. Do you expect that value goes up or down as we increase the temperature? It would go up because we got more molecules that have the ability to have enough energy to be in the gas phase. Right? So the pressure goes up as the temperature goes up. And even if we don't remember that from the graph I showed you, we also learned about the ideal gas law, and we know as temperature goes up, pressure goes up, right? So you can measure it like this, right? You can measure vapor pressure of something with one of these things. This is called a manometer. It's the same kind of mercury setup that we talked about in chapter 6. And we look at the height change. We can take a height change and use density, pressure is equal to density times acceleration due to gravity times height, and calculate pressure from that. When it's mercury, it's easy. We just read it off. How many millimeters of mercury is it? So we would just come here and say, okay, this is 37 millimeters. So the pressure of this thing is 37 millimeters of mercury, right? That's the benefit of using that millimeter of mercury measurement. You can straight read it. All right, so I ask you the question, how do we know when something's boiling? We define the normal boiling point of when that vapor pressure is equal to 1 atmosphere. That is the definition of boiling point. So if we look at a graph of pressure versus temperature, as temperature goes up, pressure goes up. When we get to the point where that pressure-temperature line touches 1 atmosphere, then that temperature is your boiling point. That's how we define it. But we know that water boils at a different temperature at the beach than it does in Denver, Colorado, right? So what's the difference there? Well, that's not normal boiling point. That's just boiling point, okay? So there's a nuance there, a slight difference there. Normal boiling point's when the vapor pressure equals 1 atmosphere. And those are the tabulated values. If you go look the boiling point up of something, on the internet or in a book like I would do, that's the normal boiling point. Boiling point, without normal in front of it, is just when the vapor pressure equals whatever the external pressure is, right? So at the beach, the external pressure is 1 atmosphere, right? But here, we're a little higher up than the beach, so our vapor pressure, our external pressure, is a little lower than 1 atmosphere. So water here boils at maybe not 100.00, but maybe 99.99 degrees, right? In Colorado, maybe that's 99.1 degrees, all right? Because they're higher up than us. So when your vapor pressure equals your external pressure, that's your boiling point. Again, all of this depends on the concept of intermolecular forces. The stronger those intermolecular forces are, the more tightly those molecules are held together. So the higher we have to raise the temperature to get those molecules to break apart and go into the gas phase. The stronger your intermolecular forces, the lower your vapor pressure is going to be. So you tell me, water versus gasoline. Which one's got the lower vapor pressure? You would say water.
What is the formula for gasoline?
That's a good question. Let's assume octane, okay? Even though in real life it's really more like pentanes. Octane. So octane is C8H18. It's another one of those hydrocarbons. Okay. So polar, yes or no? So we'd have to draw out a Lewis structure for this thing. I did say hydrocarbons are non-polar. What you'll find out if you draw the Lewis structure for this thing is all these little sticks have hydrogens on them. There's nothing polar about this thing, okay? Non-polar, so dispersion forces versus hydrogen bonding. Even though this thing weighs a heck of a lot more than water does, right? And we know this is true with the whole vapor pressure thing, right? If I spill water on the floor and I spill gasoline on the floor, which one's going to dry up first?
Yeah.
Gasoline's going to evaporate way faster, right? It's got a much higher vapor pressure. So the reason it evaporates faster is because it's closer to its boiling point, right? The boiling point of gasoline or of octane is much closer to room temperature than water's is, okay? Does that make sense? Closer we are to our boiling point, the faster we evaporate. Again, comes back to this, right? There's always some number of molecules that have enough energy to be in that gas phase. As we increase the temperature, we increase those number of molecules. So we increase the pressure. We know that we have this pressure versus temperature, and we got a curve that looks like this, and we have the boiling point when we hit 760 millimeters of mercury. We can actually define vapor pressure as a function of temperature using the Clausius Clapeyron equation. That equation is the one that's shown right here, but don't remember that one because that one's a crappy version of it. We've got a better version of it, okay? If we were to take this information and we were to plot natural log of pressure versus 1 over temperature, the slope of that line would give us the enthalpy of the vaporization. The slope of this line right here is actually delta H over R, minus delta H over R. Because that's in the equation here, right? Yeah. So this is like, think about this as, this is y equals mx plus b, or whatever, right? So m is minus delta H over R, and x is 1 over T, and y is natural log of vapor pressure. So then if I plot natural log pressure versus 1 over T, the slope of the line is delta H over R. So you can use the difference between 2 points on this line to calculate delta H, and that's the way we usually see it. This is the equation that we care about, okay? Natural log of pressure 2 over pressure 1 is equal to minus delta H over R multiplied by, and I like it better when there's the parentheses there, 1 over T2 minus 1 over T1. You will see me write this equation without the minus sign. You'll see me write natural log P2 over P1 is going to be equal to delta H over R, 1 over T1 minus 1 over T2 in this fashion, okay? I've multiplied the minus 1 through, and that switches the order of T2 and T1. So you'll see me write it in this fashion instead of the other. Here is a good question for you guys. I can't erase that stuff. So can we figure out the vapor pressure of water at 50 degrees C if we know the enthalpy of vaporization and we know the vapor pressure of water at 20 degrees is 17.5 torr? And the answer to that question is yes, but we got to use this equation to do so, okay? So what we need to do is we need to identify pressures and temperatures because that's the variables in question here. And it doesn't matter what we set as the ones and what we set as the twos, as long as we pair up the temperatures and pressures, okay? So at 20 degrees, we have a pressure of 17.54 torr. Those two have to be paired up. That can be P1 and T1, or it can be P2 and T2. It doesn't matter, but they got to be paired up, okay? The other pair would be here, say T2, and P2 is the thing we don't know, right? We don't know the vapor pressure. So then we take this equation, and we have to solve this equation for P2. So how do we solve this equation for P2? Well, the first thing I see here is that I have this whole natural log deal, and I got to get rid of the natural log, right? We talked about that on day 1 for a reason. So how do we get rid of natural log? E to the stuff, right? So I can get rid of natural log. I can write P2 over P1 is going to be equal to e to the stuff. So I'm going to write exp. That's going to be e to the, okay? And now all the right-hand side is in there. Minus delta H over R, 1 over T2 minus 1 over T1. So then to solve for P2, P2 is equal to P1 times exp stuff. Right? I want you guys to solve this for me, and that's going to take the rest of the day, okay? So I want to turn the light on so you guys can see your paper and see what you're doing. But I want you to solve this problem. People struggle with this problem. When they start putting exponentials in their calculator, they start making mistakes, okay? So I want you to actually try it and put the numbers in and convince yourself that you can do it, okay? Or convince yourself that you need to go home and try it again. Because a lot of people will look at this and go, yeah, it makes sense, I can solve it. And then the actual punching the numbers in screws them up, okay? Say again? That's a great question. What are we dealing with over there? We have pressures and temperatures, but we also have an energy term, right? Delta H is an energy term. What is R when we're dealing with energy? 8.314. So let's write that one down. Let's make sure we remember that. R is here. It's the same R, okay? The same R is in the ideal gas law R. It's just using different units now. We're using joule per mole Kelvin instead of liter atmosphere mole Kelvin. Still the same proportionality constant, just cast in different units, okay?
So can we leave partial controllers?
That's a good question. What do you think? What are the units inside the exponential? All that stuff in there, right? What's the unit of stuff? What is the unit of delta H?
Kilojoules per mole.
Kilojoules per mole, okay? What is the unit of R? Okay, so can we see that kilojoules per mole will cancel out? And we'll have a 1 over Kelvin there?
Right.
Or actually we'll have a 1 over Kelvin there, which is Kelvin. And then what about temperature over there? We got Kelvin. So those are canceled too.
Right.
So what is the unit inside the exponential? Nothing. There's no unit at all in there, right? So the only unit present is the unit of pressure. So it can be whatever you want it to be. 100%. You've got to make sure that your delta H is in terms of joules, because if it's not, it won't cancel with the R, right? Because the R is in joules. So absolutely got to convert those kilojoules to joules. What do you guys get? 83? I think 83 is right.